Hey everybody, today what we're going to be talking about is the roast. Now, when you're making a Woots ingot, you're going to first end up with structure a little bit like this, or a ingot a little bit like this, and hard to see probably in the video, but I have actually ground this little edge here, kind of at the rim. Ground a spot clean, polished it up, gave it an etch, and this is going to show me what structure I'm dealing with inside the ingot. Obviously on top we're going to have a dendritic structure, but just because we see a dendritic structure on the surface doesn't mean that's what we actually have inside. This is a case of the that initial solidification structure can be dendritic, or will be dendritic pretty much, but during the cooling after the solidification, things can change, even before we get to any follow-up treatments. And probably the most key follow-up treatment is roasting the ingot. If we look back at the articles written by Verhoeven and Pendray, they talk about roasting their ingots. They use a couple different techniques during the course of their experiments. And if we look at historical records and historical accounts, there are definitely references to the ingots being treated in some fashion before forging. If you take your Woots ingot right out of the crucible, toss it in the forge, heat it up, and start trying to forge it, the likelihood of failure is very high, because even if that dendritic structure has changed during the cooling, there are a lot of things going on in there that you may not want when you start forging. So here are a couple pictures of what that little window can look like, to give you an idea what sort of the two most likely things are that you will see. So now, what is the roast? The whole idea here is to change our initial structures, the initial internal structure of the ingot, in a way that A, makes it easier to forge, and B, maybe contributes to what type of patterning we get. Now, we saw in those pictures there were two very distinct types of structures we could have. One was, pretty clearly a very dendritic structure. It's that very blocky, square structure. While the other was a mixture of grain boundary carbide, sometimes just referred to as GBC. So mixture of GBC and acicular carbide, which basically just means, or Widmanstätten carbide, which basically just means needle-like carbides. And those form actually within a grain, as opposed to grain boundary carbide, which obviously precipitates along the outside of the grain. Then that dendritic structure that you see in one of the photos, essentially all ingots have that structure at some point during the cooling process. As we are coming down here through, I didn't really draw in the full liquid and then slushy zone, but as we're coming down through the slushy zone, what we get are the dendrites of relatively pure iron, which has a higher solidification temperature, and that is growing into the liquid. And in between those fingers of dendrites, we're trapping liquid that liquid and the liquid that they're growing into is increased in carbon and, generally speaking, most of the sort of trace elements or third elements you're going to have in your mix. So basically, the best way to imagine it is that you have this almost pure iron dendritic structure that is growing, and then it is trapping a higher concentration of almost every other element in between. In this illustration, the dendrites are growing towards us, and we can see that the T-shaped dendrites in the center successfully grow in layers outwards, eventually trapping the darker, higher concentration material in between. Now, in Woots and also in most steels, some of those elements are very strong carbide-forming elements. So things like vanadium, very strong carbide-forming element, also sometimes referred to just as CFEs. But you can also have slightly weaker ones like tungsten or chromium or molybdenum. They're still strong carbide formers, but they may not form carbides at quite as high a temperature. But they are being concentrated between the dendrites, and carbon is also being concentrated between the dendrites. So as we're cooling here, and then finally reach full solidification, the structure we're going to have is the pure iron dendrites with these pockets of much higher carbon and higher CFE concentration. And what that results in are very large, pretty blocky primary carbides. So if you etch and you get that, if you etch that little window on the ingot and you get that very dendritic structure, very likely those are actually the primary carbides. Those carbides formed essentially during and right at solidification, or sort of full solidification. But we have a lot of space here before we actually reach the temperature, because remember, this is what's called the ACM line, which it basically means this is our cementite line or carbide line. This tells us where we are really going, where the steel really wants to start precipitating carbide. So as we're cooling through the austenite zone from full solidification down to the ACM line, during that entire period, carbides are dissolving. We are above the point where we're above the temperature where they are really stable. And so those primary carbides are actively dissolving as we come down. And then when we hit the ACM line, carbides are now stable. We're now in a temperature range where those carbides are actually stable, and they begin to, and we begin to precipitate carbide again. Now, what keeps us from just instantly dissolving all that carbide, all that primary carbide? And the answer to that is sort of twofold. One, we have a carbon concentration issue. During solidification, carbon concentrated or segregated along with the other elements. The actual amount of carbon that austenite can hold is 2.2%. And what this means is that where we have higher concentrations of carbon, we actually, the carbides can't dissolve. There's no place for that carbon to go. So it's a slow process because first carbides need to dissolve and carbon needs to diffuse away. At this very high, at the very top end of this range, carbon is diffusing very quickly. by the time we reach the bottom end of that range, carbon is now diffusing very slowly. And what this means is, or let's say, this is why you can have different structures resulting from very similar chemistry in your ingot. It doesn't take a lot of change in chemistry or a lot of change in the cooling rate to greatly affect what type of structure you see. As we're cooling from point A here, where we have those primary carbides, they begin to dissolve until we reach ACM. Now, if we have dissolved all of the primary carbide by the time we reach ACM, then we are likely to get grain boundary carbide and possibly that sort of needle-like Widmanstätten carbide that will precipitate as we continue down. If, however, we have not dissolved all of our primary carbides, that very dendritic, blocky structure, the carbon is likely to just reprecipitate back onto or in the vicinity of those existing carbides. That's something kind of key to know here, is that carbides like carbides. So if you have carbide present, then new carbide is likely to precipitate on it or nearby. This brings us to the roast. That grain boundary carbide structure isn't necessarily bad, because what it tells us is that our carbon diffused pretty much completely. So we had a relatively even carbon content throughout, and then we precipitated grain boundary carbide, which isn't something we want in our final knife or sword or whatever it is. Grain boundary carbide is a terrible structure when it comes to actual physical characteristics. However, the fact that the carbon is relatively evenly dispersed, definitely a lot easier to forge at that point. However, if you look at that grain boundary carbide, you'll realize that the grain structure in the ingot is huge, absolutely enormous. And we really don't want that. Another aspect of that is troublesome is that the grain boundaries probably still follow fairly closely with the dendritic structure, that solidification structure. So if there were imperfections in that solidification, our grain boundaries probably still align with them fairly well, and that makes for a pretty weak structure overall. Other side of that dendritic structure with very large blocky carbides is going to be incredibly difficult to forge without having fracturing in your steel. Carbides themselves do not forge. They can move in the, kind of within the iron matrix, but they are themselves not at all malleable. So if you have that very dendritic structure, if you were going to just go straight to forging, it's going to have to be some pretty delicate forging. So, to the roast. I've included two versions of the iron-carbon phase diagram to help illustrate the discussion of the roast. Now, referring back to some of Pendre and Verhoeven's work, at least at one point in time, they were actually doing a very long roast at 1250 centigrade. And that is really the limit of what you can do before you start going back into the mushy zone or slushy zone of having partially melted material. And they were doing this roast for 12 hours, sometimes more. And they were putting the ingots back in a crucible that was lined with iron oxide, because they were, in addition to the heat aspect, and changing the internal structure, they were also trying to create a case of decarburized material. And part of the reason for this was that looking at historical ingots, many of those ingots had high sulfur contents. Higher sulfur contents lead to hot shortness, and that hot shortness kicks in right around the ACM line. Although, quite honestly, I believe it is sort of like the 2.2% carbon line. I believe that the sulfur hot shortness line is also a straight line across. I'm not as sure about that. However, hot shortness was an issue, and what they part of their goal was to replicate how historical smiths might have created this case of extremely low carbon steel or iron, sort of as an envelope on the outside of the ingot. Now, in the process of oxidizing the outer portion of the ingot, you do also oxidize out the sulfur. So they were creating a case or a jacket on their ingot that was very low carbon, very low sulfur. Other thing that's going to happen in that process is, we are obviously roasting. If we're at 1250, we are well above the ACM. By the way, this little dotted line is 1.5% carbon, which, obviously some Woots has more carbon than that, some Woots has less, but that's a pretty good midline of where historical Woots fell. Was a little bit above or a little bit below, or a range around 1.5%. So if we're at 1250 C, we're clearly well above the ACM. And that means that a long roast at that temperature, you will diffuse your carbon completely. You will have no remnant structure or remnant carbides from the initial solidification and cooling. Some of the historical accounts refer to ingots being set into a forge, into a charcoal forge, brought up until they were glowing. Hard to know exactly how hot. As I recall, the account talked about them being red, but a lot of historical accounts refer to anything up to white being red. So you had dull red, strong red, bright red, all kinds of different descriptions for red. So not real helpful in terms of knowing exactly what temperature that might have been. This was also written by an observer rather than the smith, so that also adds in a little bit of murkiness. Was the observer being shown a real process or a fake process? Hard to know. But in either case, the idea that they were going with, apparently, was they would heat and roast the ingot in the forge for a while, bring it out, put it on the anvil, give it a tap, hit it, obviously not with your hand, hit it with a hammer, get an idea what it sounded like, what it felt like, and then the smith would evaluate, did this feel or sound ready to forge? Was the ingot good to go? If not, back to the forge, keep going through that process. And there are a couple good reasons for a process that works in that fashion, especially historically speaking. One, probably the most important reason is that the ingots the historical ingots would have been quite variable. The carbon content would have been quite variable. Many times the smiths, actually in almost all cases, the smiths were not making the ingots. They were just getting the ingots, purchasing them, and then forging them. And there were a number of different locations where ingots were made. So you might be getting ingots from different places depending on where the latest trade had come from. So having a process in which you roast the ingot for a while and then test it, does it feel like, do I feel like it's going to forge now? That gives you the opportunity to, in essence, adjust the, not just the structure of the ingot, but also to some degree the chemistry of the ingot, because that whole time that it is roasting, it is losing carbon. And if we assume that carbon contents in the ingots varied, it could be that you were going to occasionally get a much higher carbon ingot, but through that roasting process, you're going to at least bring that carbon content down somewhat. And especially if you allow the roasting process to continue as long as necessary to create that forgeable ingot, you're going to even out some of that variation with this follow-up process. For most modern smiths who are making crucible steels, the chemistry of the ingots and the cooling rate of the ingots is probably going to be a bit more consistent than you would have seen historically. So, to a greater degree, you can establish kind of a set protocol of, I'm going to take my ingot and treat it in this fashion to, every time. And that gives me the same starting structure when I go to forge. And again, just kind of referring back to the chart, or to our phase diagram, the kind of the key things to keep in mind here are going to be, what your assumed carbon content is, and therefore where your ACM line is, and kind of similarly, where does your slushy zone start? Because if you roast up into the slushy zone, my opinion is that's not going to do you any good. Once you get up into the slushy zone where you're getting partial liquid in there, basically what you're going to be doing is just replaying the initial solidification process. So not going to necessarily be super helpful. Regardless of exactly what temperature you choose to roast at, one thing that almost certainly will happen is you're going to change the grain structure of your ingot. And that change in grain structure helps lead to better forging. Now, I have done roasts from half hour all the way up to 3 hours. There are definite differences in there. At a half hour, I definitely there was more forging difficulty than at 3 hours. That doesn't mean you need to go to 3 hours. And depending on what your ingot is like, half hour might be perfectly sufficient. However, I do suggest doing some kind of roast before you start forging, so that you've changed that initial grain structure at the very least. Because like I was saying before, when you start out, the grain structure and the dendritic structure are pretty closely aligned, and that's a very brittle setup. So at the very least, you want to change that initial grain structure so that it's no longer aligned as closely with the dendrites. Now, a couple follow-up points. One, I do suggest not roasting just below ACM. Specifically not with an unforged ingot. And the reason for that is that the initial ingot is rather porous, and right in the same vicinity where carbides precipitate, so along or just below the ACM line, is also where graphite precipitates. If we look at historical blades, many of them actually have graphite in the blade, and that graphite essentially replaces carbides. And once it's in there, it's essentially impossible to get rid of. So you really want to make sure, if you are going to be sitting in that temperature range, right around the ACM, you want to make sure that you have first consolidated your ingot to close up that initial porous structure, and therefore avoid getting a huge amount of graphite in your blade. Graphite has a lot of great characteristics, but not for swords. If you think about pencil lead is graphite. That is not something you'd want in your sword. First piece of advice there. Now the second item I'm going to talk about quickly is nickel. You really don't want to add any appreciable amount of nickel into a very high carbon, into a hypereutectoid steel. And the reason for this is, again, graphite. Nickel actively pushes carbon out of solution to create graphite. Now, that's obviously not a good thing. We don't want graphite, and any carbon we lose as graphite is carbon that doesn't get to become carbide. You can offset this to some degree by adding more of those carbide forming elements, particularly ones that form carbides at higher temperatures. And what those do is, as you're cooling down, as we're coming towards the ACM line, the carbides form first, and then maybe you get graphite. So having those carbide forming elements can help mitigate nickel content. So anytime that I'm doing an ingot where I'm adding meteorite or something like that, where I'm going to have nickel in the ingot, I always bump my CFE levels a little bit to offset that some. Another thing, just quick note, when you are looking at the ACM line, handy thing to know, so we start off at the eutectoid point at about 0.8% carbon, and we the ACM line ends at 2.2% carbon, which is kind of theoretically where we start getting into cast iron. Now, so we have carbon contents, and we also have temperatures for those lines. And the kind of fun thing about that is we know that if we know our carbon content, or roughly know our carbon content, and we then know what temperature we're at, we can actually know how much carbon should be in solution and how much carbon should be remaining as carbide. There's obviously a bit of a delay in switching from one to the other. Carbides don't precipitate instantly, nor do they dissolve instantly. So there's delay involved in this. But if we're looking at, if I have a 1.5% carbon steel, but I have not reached the ACM line, I can essentially draw a line over to the ACM line. And where I am on the ACM line is going to tell me how much carbon is in solution, how much carbon is still as carbide. So it's a really handy thing to know, and you can keep in mind when you are choosing your forging temperatures, because that will tell you about how much carbide you have present. My finding has been that too much carbide in the steel during forging clearly going to make it harder to forge and makes it more likely to fracture. So obviously I didn't address the exact roast that I use. Every smith that I have talked to uses a slightly different technique. They use a slightly different roast, different temperature, different period of time. But they're all based on the same thing, which is the idea of changing that internal structure prior to forging. And possibly changing, or almost certainly changing, how the carbon is situated within the steel before they begin forging. Obviously, that sort of secondary concept of decarburizing the outer shell, that's going to happen in almost any roasting situation. I will note, actually, one thing about roasting. If you decide you're going to roast back in the crucible, keep in mind that depending on what type of crucible you're using, like let's say you're using a clay graphite crucible, you're going to actually pick up carbon from the crucible during that roast. So in that situation, you might want to do what Pendre and Verhoeven would do, of packing it in iron oxide to avoid picking up carbon from your crucible. So that's the roast for now. Like I've said before, if you have questions, feel free to ask in the comments here on YouTube, or you can swing over to my Instagram page and ask questions there. It's @PeterBurtKnives. Hope this helps.